In this next section, 24.2, we'll be using these concepts to look at the simplest of all capacitors, that of a parallel plate capacitor. We'll take two parallel plates, and we're going to imagine that these plates are essentially infinite or extremely large in every direction, both of these. And we're going to put a charge on this and an equal and opposite charge on the other one, exactly like we would have done here. In other words, we start with two neutral plates and begin taking charges from one and putting it on the other. Now, what we want to do is we want to understand what the capacitance is. And we know that the capacitance is the charge divided by the voltage. Just as I've written here, capacitance is charge divided by the voltage that's created when that charge is moved between the two plates. Now, I can't talk about the total charge here as much as I can talk about the charge per unit area. So I'm going to say let there be a charge sigma, which is the charge divided by the area over this whole plate. And that way the plate can be larger and larger and larger, but sigma can be constant. It's how much charge is in a square meter. So I'm going to write this formula for capacitance as Q is equal to sigma times A. Q is equal to sigma, charge per unit area, times the area. Now I want to look at the voltage. And if I look at the voltage, you will recall that we had an equation that said the voltage was equal to the electric field times the distance. Voltage was equal to electric field times the distance. More precisely, the infinitesimal, you recall that we wrote it as an infinitesimal voltage change, was equal to E dotted with dr, where these were two vectors. But we can forget that for the time being and look at the symmetrical situation of what the voltage is between the two plates as the electric field times the distance. So we're going to write this as electric field times the distance. However, you'll recall that for a parallel plate capacitor, the electric field was equal to sigma over epsilon naught. We derived that previously when we looked using Gauss's law at the electric field that exists between two plates. If we make this one positive and this one negative, you recall that the electric field goes from the positive and disappears at the negative. So now we can plug this in and write this capacitance as sigma A divided by the electric field is going to be sigma over epsilon naught times the distance d. And now the two sigmas will cancel one another, and so what we end up with is epsilon naught in the numerator times A divided by the distance between the two plates. And this is an important formula. The capacitance of a parallel plate capacitor is epsilon naught A divided by the distance between them. This, of course, will be a key formula that you would have on your quizzes or exams. Now, if I use different combinations, for example, if I used a cylinder inside another cylinder, I would get a different answer from this. And if these objects had some strange shape, like so, and here are objects A and B, or like these objects up here, then I would end up with different formulas. So this formula only works for the parallel plate capacitor. In a more advanced course, we would actually do computations like compute the capacitance of two cylindrical conductors. But we're not going to do that here. We're just going to look at this one capacitor formula, require that you know this. But now, the other capacitances we will simply look up, or they'll be given to you. We now want to look at the problem of how we combine capacitors together. There's a symbol for a capacitor, and the symbol for a capacitor is given by this symbol right here. It looks like the parallel plate capacitor in a way. And of course what we do is we push charge onto one side and pull it away from the other side. So we'd use something like a battery to pull it off of here and push it over here. This is the symbol for a capacitor. Now we want to imagine that we have several capacitors, and we're going to take these capacitors and connect them in what is called parallel. That means all of the left sides are connected together and all of the right sides are connected together. And if this has a capacitance of C1, this of C2, and this of C3, we can ask the question, what capacitance would we get for a system? No matter what these are, if those are the capacitances, what system would we get if we combine those together in a parallel way? The answer is that C parallel is equal to C1 plus C2 plus C3, and if I have more, plus C4, and so forth. So when capacitors are added in parallel, they simply sum up. And if you had a problem on your test and you had to compute that, then you would simply add the capacitance of 4 to 3 to 2, and you'd say 4 plus 3 plus 2, and your capacitance there would be 4, 5, 6, 7, 8, 9. So your capacitance of this whole system would be 9. Now, if on the other hand these capacitors are connected in series, which means I have one capacitor here, another capacitor here, another capacitor here, and so forth, and this is capacitor 1, capacitor 2, and capacitor 3, then it turns out that the capacitance of this whole system has a reciprocal that's equal to the sum of the reciprocals. Oops. A very, very different formula than the one we just looked at. And so if we again had these same capacitances, 2, 3, and 4, the capacitance of the whole system in series would be equal to 1 over 2 plus 1 over 3 plus 1 over 4. As 12 is the common denominator here, this would give us 6 over 12, 4 over 12, plus 4 over 12, plus 3 over 12. And that would give us 13 over 12, and that would be 1 over the series. Now, because it is very often that we observe students that leave this and think that that's the result. It's not. The capacitance to be in series is the reciprocal of this. So C series is equal to 12/13 in this particular case. And this is the formula that you would use. So the dominant equations that we have that you need to remember for the test are the unit for capacitance, the definition of capacitance, a general understanding of where capacitance comes from, the formula for the parallel plate capacitor, capacitors in parallel, and capacitors in series. Finally, in this section, we look at the energy that's stored in a capacitor. And you see here in this formula, the energy, W, we're going to write it that way, energy stored. When we charge a capacitor, the energy that's stored in a capacitor C is given by 1/2 of Q times V. Now that's the total charge times the voltage. Now we can rewrite that, since we know that the charge, you recall that C is equal to Q over V. It follows that Q is equal to C times V. So this is C times V, so this is 1/2 C times V, so it's 1/2 CV squared. I think this is an easier formula to remember. Nothing's to any power. It's just the charge times the voltage, and that gives us our energy, whereas the capacitance is the charge divided by the voltage. This, of course, is going to come out in joules. And so if we put a charge of 4 coulombs on a capacitor, and we had, let's say, 12 volts. This was done by, say, a car battery, 12 volts. Then the energy that this battery, capacitor would have, would be, or the work, that's why we use the symbol W, the work that it would take to charge this capacitor would be 1/2 times the charge times the voltage, or 12 times 2, or 24 joules.